Welcome to this explainer on system survival. Look, if you're operating at any kind of scale, you already know the harsh reality. Microservice failures, they aren't just unexpected bugs. They're literally inevitable digital contagions. The real question isn't if a service is going to fail, but when and exactly how your system reacts when it happens.
Right off the bat, there's a massive mindset shift we have to make. The goal isn't to prevent failures. We need to drop that naive hope of writing absolutely perfect code and wake up to the hardened reality of fault tolerance. You can't control the network, right? But you absolutely can control your application's blast radius.
So let's jump straight into phase 1, the threat of cascading failures. To really understand the defense, we've got to look at the threat itself. How do modern distributed networks actually die? Well, usually it isn't some massive dramatic server crash. It's way sneakier than that. It's death by 1,000 creeping timeouts. Just picture how a cascading failure actually plays out. You've got a minor latency issue popping up in some obscure downstream dependency. Because it's slow, your calling service just sits there waiting, and eventually it exhausts its entire thread pool. And then, before you know it, completely unrelated services start crashing just from resource starvation. It's wild. This tiny little bottleneck rapidly metastasizes, and boom, it brings down your entire application network.
To really wrap your head around this, think about the electrical circuit in your own home. Martin Fowler actually coined this analogy, and it is spot on. If a faulty appliance draws way too much current, it's literally going to burn your house down if the physical circuit breaker doesn't trip. Well, in that exact same way, a blocked or a lagging microservice will completely incinerate your system's resources if you don't step in and cut it off.
Which brings us to phase 2, the circuit breaker pattern. This is the software equivalent of that crucial hardware safeguard. We desperately need a pattern designed to completely sever the connection before the damage spreads everywhere else.
So what is it? A circuit breaker is a fault tolerance mechanism that dynamically interrupts requests to a failing service. Think about it. Instead of hammering a dying dependency with endless retries, which honestly just makes the problem worse, this pattern temporarily stops all traffic. It prevents a massive system overload and gives that failing node the critical breathing room it needs to recover.
Now, this context totally flips how we need to view retries. You absolutely cannot just implement retries blindly. If you do, your so-called resilience is actually going to trigger a catastrophic retry storm. Safe retries require a whole combination of building blocks. We're talking strict timeouts so you fail fast, exponential backoff with a little bit of random jitter so you aren't overwhelming the network, idempotency, retry budgets, and yeah, of course, circuit breakers.
Okay, moving to phase 3, closed, open, and half-open states. See, a circuit breaker isn't just a simple on-off switch. To implement this containment protocol effectively in your code, you have to navigate a life cycle of 3 very distinct dynamic states.
State 1 is closed. Now, counterintuitively, closed actually means everything is perfectly fine. Think of it like a real electrical circuit. The circuit is closed, so the current, or in our case, the data, is flowing smoothly. Under normal operations, requests just flow right through. But the breaker is silently watching the error rates, just waiting to see if a predefined failure threshold is breached.
But once that failure threshold is exceeded, the circuit flies open. In state 2, all outbound calls are instantly rejected for a strict cooldown period. We don't even try to reach the downstream service. We just return a failure or a fallback right away. This protects the caller's threads and lets the downstream service take a desperate moment to stabilize.
Finally, we reach state 3, half open. After that cooldown timer expires, the breaker doesn't just throw the gates wide open again. That would be a disaster. Instead, it carefully lets a really small, controlled number of test requests slip through, just a probe for recovery. If those test calls succeed, awesome. We trust the service is healthy again and close the circuit. But if they fail, we snap right back to the open state immediately, and the cooldown starts all over again.
Let's look at phase 4, weaponizing .NET with Poly. Look, understanding the theory is great and all, but how do we actually apply this stuff? Well, in the .NET ecosystem, we definitely don't build these defenses from scratch. Instead, we weaponize the industry-standard resilience library, Poly, to stitch these patterns directly into our HTTP clients.
You know, your use of Poly should actually evolve right alongside your engineering maturity. A junior developer, for instance, grasps the concept and stops infinite retries. A mid-level engineer configures Poly via dependency injection, combining retries and circuit breakers together. But a senior engineer, they take it to another level. They design advanced resilience strategies, architect bulkheads, and actively monitor service-level indicators in production.
Speaking of which, for true isolation, senior engineers deploy bulkheads right alongside circuit breakers. Think of watertight compartments on a massive ship. A bulkhead rigidly caps the exact number of threads any one service can consume. If the quota is full, Poly throws a bulkhead rejected exception. This ensures that a leak in, say, your product review service doesn't sink your entire checkout process. The healthy parts of your application stay lightning fast.
Which brings us to Phase 5, chaos engineering and testing. Because, honestly, just having the armor is not enough. You can write the most beautiful policies in the world, but you must proactively fire live ammunition at your architecture to see where it actually breaks.
And that brings up a massive challenge. How do you actually test these resilience policies? Standard unit tests are just not going to cut it here. You have to actively validate how your application responds to sudden, violent state changes, like a circuit snapping open out of nowhere or a retry budget getting totally exhausted.
The difference between the two approaches is stark. Normal testing asserts a specific return value in a complete vacuum, assuming ideal conditions. Chaos engineering, on the other hand, verifies your system's steady state and survival by injecting deliberate digital poison. We're talking injecting sudden latency or taking nodes completely offline in production-like environments. It proves your circuit breakers actually trigger when the pressure is really on.
In the .NET world, you do this by integrating Poly's chaos tool, which is called SIMI. Injecting chaos exposes these terrifying things called zombie states. These are scenarios where a service is technically alive, but practically totally useless. A simple 2-second downstream delay might silently exhaust your connection pools and paralyze your entire application. SIMI helps you hunt these zombies down before your users even notice them.
Ultimately, bringing circuit breakers, bulkheads, and chaos engineering together shifts your entire engineering focus. You stop asking, does the code work? And you finally start asking, does the system survive? Because in the unforgiving landscape of distributed microservices, elegant code means absolutely nothing if your architecture cannot contain the blast radius. So looking at your own architecture right now, if your most critical dependency failed this exact second, what would your blast radius look like? Thanks for joining me on this explainer, and keep building systems meant to survive.